Hello, everyone. Welcome to another episode where I do the reconstruction of the game of Go written by Jonathan Kim Millen, as it has been described in the Byte magazine of April 1991. So there was an article describing how to create your very own game of Go. And a couple of previous videos, we've been handling the I/O routines to print the board, to get the user input from the key1 keypad. So for those who maybe forgot or don't know this, I want to recall that we are developing in 6502 assembly for the unexpanded key1. So this is the picture of the key1, and this is my JavaScript emulator of the key1. And I'm not using any tools for automating the process like assemblers or text editors. So I write the code on a piece of paper with a pen, and then I just put those from the paper to the text file. I do hand assembling, which means that I turn assembly mnemonics like LDA, SDA into 6502 opcodes using the table that I've been showcasing in the previous videos. And finally, I do manually enter the opcodes into the key memory. So the left four digits are standing for the address. These two stand for the data. And that's how the program is being developed. For the sake of simplicity, I'm using the paper tape format to upload the data that I've already typed in and debugged and checked that out. So we would be using the paper tape format. But before that, I would like to walk through the pseudocode of what has been implemented recently, and then through the particular assembly listings that implements this particular pseudocode. And then I will load the paper tape of those bytes being assembled along with the I/O routines as well, so essentially the entire program, and would show you how the count routine is working. So today we're going to have a look at the count routine, which does the following. So it finds the stones connected into the group, and it marks the liberties of that group, and it also maintains the count of those liberties. So why is that needed, you might be wondering? So that's needed in order to handle captures in the game of Go. So the group that does not have any liberties left is going to be captured, which from the internal board representation essentially means you need to vanish those stones from the board. So how do we know that? If the number of liberties is equal to 0, then we know that the stones should be removed. And along the way, we do mark the stone. So let's first have a look how the count routine is working based on the pseudocode, and then we'll go to the 6502 assembly. So count is a recursive function, which means it's calling itself to find those connected stones. So we can start with a simple condition. If we hit the board edge, or in other words, if we find ourselves in the off-board square, so this is done by looking at the square index. In this case, we just return, okay, because we're not going to look further on because we have already reached the end of the board edge. Otherwise, we do have two scenarios. So the first scenario, if we do encounter a stone, this is the scenario, and this is the scenario. And another scenario is when we encounter an empty space. So if there is no stone at X, which essentially means that there is an empty space, which is marked as period, the hexadecimal code 2E, ASCII code for the period character. So we may either have a stone, which may be marked as traversed or not marked as traversed. And we also have an empty square, which we then would mark as a liberty, okay? And by the time we're marking the empty square as a liberty, we also increment the count of liberties. Okay, so the most interesting part happens here, essentially, within the scenario where we did find a stone. So if we did find a stone, then we need to make sure that the stone matches the color we're searching for. So say we're searching for a black group, then the next stone that we've just found should be black. If we're searching for the connected white stones, the next stone that we've just found should be white. Otherwise, we just return. And also, we need to make sure that the stone is not marked. So what is this? So in order to avoid like counting stones many times, once we've counted the stone, we mark it. By marking, we mean setting a specific bit, essentially converting the uppercase letter representing the stone to the lowercase letter. Okay, and then we recursively call the count. So this is the heart of the. So this is the variation we may solve an algorithm at some point. So what we do here, so north means current square x minus the board width. So essentially x minus 16, yeah, because we have a 16 by 16 board. Okay, east. Okay, let's do south first. So south means x plus 16 plus the width of the board. East going one square to the left, so essentially x minus 1, and west, east is x plus 1, and west is x minus 1. So x minus 1, x plus 1, x plus board width, x minus board width. So these are the directions, and the color remains the same by the time we're recursively traveling through the connected group of stones. So looks to be very simple, but unfortunately it takes a bit too much of code to implement. Eventually, this took me 72 bytes to code this routine. But anyway, let's go step by step to enjoy the 6502 listings here. So, at the address of hexadecimal 0286, which is the next address after the previous routine, which, if I'm not mistaken, is handling the user input, has ended at 0285. And the next empty byte is used to store the color, the changing color. So the color that we are looking for, so essentially this color is we're storing the argument for a function. And the square x would be living in the x register. So we have x and y registers and a register in 6502 assembly. So x register is holding the current square. Then the color is stored in the memory in here, this address. And also we're using the y register to keep track of the liberty count. So we can start with setting y register to 0. Essentially, this means that we reset the liberty count every time we call count. But interesting thing here is that the recursive call would be calling count from here, count recursive, while the first time we run count would be calling it at this address, count liberties. So in the main loop, we'll be calling the 0287 the first time, and within the count routine itself, would be recursively calling not this one, but instead we would be recursively calling this one, so that liberty count does not get reset every time we do the recursive call, because we need to aggregate the liberties. Hopefully that makes sense. So we kickstart with resetting the liberty count, then clearing the carry flag. So this part is looking for off-board squares. How it does it? So in case if, so we're comparing the X register, which contains the current square. So we need to make sure that before running this function, the X register already contains this current square we want to start finding the connected stones from. Okay, so in the main loop, we'll be setting up the X register to point to the certain square we're interested in. Okay, and based on the value of the X square, this may be on board or off board. So we're comparing the X square with a hexadecimal value of 10 decimal 16. Yeah, 16. And in case if the carry flag is cleared, we return from the function. So we remember that the values from in the 0 page from 00 to 0f are occupied by the board coordinates, ASCII values for board coordinates. So if the board square if the index is from 0, 0 to 0f. In this case, we know it's like goes below that where we're interested in. So that's the offboard. So essentially, this condition sets the carry flag accordingly. So in case if we have if the x is like on the in the range within the range lies within the range from 0, 0 to 0f. In this case, we know it's offboard, and we jump to the return statement. Otherwise, we transferring the value of the X register to the A register and comparing this with 0f. So we are asking if there is an f in the right 4 bits, the least significant 4 bits in the square index. So it might happen that the value of the index is 0, 0, but this is handled here, then 1, 0, okay, 2, 0, 3, 0, 4, 0. So all those are offboard as well, and they do handle, they do hold the value of the row respectively. So with this bitwise AND operation, we know if we encounter squares like 1, 0, 2, 0, 3, 0, etc. And those squares, so in case if we bitwise AND with 0f, so in case if that's the case, then the 0 flag would be set, and we know that we are in the offboard square, and we just jump to the account return to return from this routine. Okay, then we need to meet the criteria of that we have the stone that is not an empty square. So assuming that the x holds the current board in the board square index, and assuming this index is not offboard, because otherwise we would not ever get here. Okay, so we're loading the value at the 0 page indexed by the x by the square, so board indexed by the square, and if that value equals to 2e, which is the ASCII character of period, this means that this is an empty square. In this case, we need to branch to the label mark liberty, where we do the following stuff. So within the mark liberty, we just load in the value of ASCII character plus to the A register and set it to the board, and also increment the Y register. And with this instruction, we increment the count of liberties. Okay, and we also know that the square on board is assumed to be a liberty, so it's not going to be like counted anymore. Okay, but otherwise, if this is not the case, this means that if we didn't jump here, then we get here, and this means that we get a stone. This stone might be either white stone, black stone, or marked white stone or marked black stone. So first we compare with the color, so just to make sure that the stone is the color that we need. And I'm wondering, I just thought that, yeah, since the color is set as the stone code, that particularly we don't really need to check this bit later. Yeah, this needs to be checked out. Yeah, I need to. Sorry, I cannot answer this question in live mode, so yeah. So just following the logic. Yeah, maybe this is a redundancy. Maybe this 4 bytes could have been saved, but anyway, at least this makes it a bit more clear, like exactly following the pseudocode. So we are asking if the value at the A register is exactly equal to the value at the variable C color that we set in the main loop before calling the count function. And if that is the case, then we're fine. We are going to check for the next condition. But if not, then this means that this is either the stone of the different color than the color we're looking for, or this is a stone already being marked with the marker that represents the stone that has been traversed already. Okay, so in this case we just return. Another condition, we are asking if the certain bit, so the 6th bit, is being set within the stone, and if it's not being set, like if it has been set, this means that this stone has been traversed already. So then we just branch to the end of the routine. Otherwise, we have a stone of a color that we're looking for, and we are about to traverse it now. We are about to mock this stone. So the first thing we're going to do next is to mock the stone. Because after this end operation, the value of the A register has been changed, we need to refresh it. So we load in the value of the stone to the A register one more time. Then we bitwise OR in with the value of hexadecimal 20, setting the 6th bit, and essentially, this is the bit that is responsible for upper lowercase in the ASCII character encoding, and this is nice because we can see the mock stones when the board is printed as the lowercase letters, and this is very cool and efficient way. Then we store this newly mocked value back to the board indexed by the X register. Okay, and then we need to do our recursive calls for the count routine. So first we go to the right, so this is essentially east, yeah, going east, so incrementing the X register by 1. So now the square we're looking for is not X but X plus 1. Then we jump to subroutine to count register. We're not going to count L, which is count liberties, the very initial, but count recursive here, because we need to preserve the liberty counter. Okay, so it aggregates every next call. So once we have done this, once we've got back, no matter how many stones we have to the right. So if we have 1 stone to the right, this is going to be called once. If we have 2 stones to the right of a given stone, we're going to jump to twice, etc. So anyway, after this, we just decrement the value of X register to, so it's equal to the original value again. After we decrement one more time, so now this is the value of X minus 1, so this is going west, yeah? So here we went east, this is going west, so going like X minus 1. Then again, we jump to subroutine. Okay, and then we could also do, like after doing this, we could do increment X, but just to save some bytes, since we're going to add, not add, now we're subtracting. We want to subtract the value to going north, so minus board size. So transferring the value of X register to A register, clearing carry, subtracting 0E, transferring back the value of A register to X register. And now, at this point, we have the value of X minus board width. And again, we jump to subroutine. And after here, we do the same, and after this operations we have the value of like X plus board width, and again we jump to the count for the very last time. And after this we need to make sure that again, like similar operations, the idea behind this one is to make sure that after we exit from the count routine, no matter how many stones were there within the connected group, we need to make sure that after everything is done, the value within the X register would be exactly the same as it was before we call the count routine. All right, and then this is the fancy way to avoid absolute jumping. So I'm just clearing the carry and do branch carry clear. So this is just a portable code. Otherwise, I could say jump into the absolute address, but here, like the amount of 3 bytes for this, 3 bytes for jump and the absolute address, but this is a more portable way of writing code. Okay, so after we're done, we jump to return. And I've already covered how the mock liberty is working, yeah. So here, again, we're just going back. So in here, finally 60 return from the subroutine. Okay, now we need to make some preparations to make this count routine working. So I've changed the main loop slightly a bit since the last video. So here, the program start. So we just do some cleanups, clearing the decimal flag to make same behavior of SBC and ADC instructions. Added some track with carry. And then we clear the board, initialize for coordinates. Okay. Then we set some stones. This is important phase. We set the stones we are supposed to be calling count on the group of stones that we are setting in here. So loading the value of 4f, which is the uppercase O letter. That's the representation of the white stones, user stones, yeah. And we set them to the squares 22, 23, 24. So like 1, 2, 3. Okay, and then we enter in the program loop. So we print the board. We're listening to the user input. Then we set the value of the value of the X register to 22. Yeah, I forgot to add explanations here. So this is like LDX, the instant value of 22. LDA, the instant value of 4F. And then we set the value we have in the A register 4F to the C color, the address 0 to 86. I need to add this, I forgot to add those. And then we want to jump to subroutine count liberties, not count recursive, not count R, but count L, count liberties, because we want to, when we're doing this, we also reset the liberty count. So that's quite important. And then the jump back to this prog loop, essentially. I'm not specifying the addresses because this might be, currently this is 0300, but later this might be like literally whatever place. I'm not sure which place this would be in future, so I'll just leave this axis because I don't know the addresses. Okay, so there is one tricky part here. It's like when we do this loop back here and then say we stop the program, probably because of we are calling some system routines that are called within the user input or due to some other unknown reason, the values are dumped to F3, F4, and F5 in the 0 page, which corresponds to A, Y, and X registers, gets messed up a little bit, so we cannot check whether the liberty count is working and whether the square in the X register has been preserved or not. So we would be temporarily putting 0, 0 here to break to see whether the square we used as the argument to the count is working properly. Okay, and also we would check whether the Y register would be containing the number of liberties that we're interested in, that which essentially represents the number of liberties that the group has. And then when that is okay, then we will just run it. I keep this 4C back, and then I would just be trying to set the stones into different positions, effectively showing how the count routine works and how it handles the off-board squares as well. Okay, so I just want to put the paper tape here. So this is the paper tape format representing all those bytes that we just had a look at in the form of listing. So I just do the import tape, paper tape. It uploads at 0 to 00 hexadecimal, and that's where the print board starts, but the main loop starts at 0300. And again, I want to go to, so losing 4F to the A register, setting the value, setting to the 0 page. So at 22, we set the white stone at, we set the white stone at 23, at 24. Okay, 200002. So this is called print. 25A02, this is called user input, A222. So this sets the X register to the value 22. This is the argument for the count routine. Okay, A9 for F, AD 0 to 86. So we just set the value of 4F to the address 0 to 86 because we're looking for connected white stones. Okay, and then we call the count routine 20 0 to 87, call the count routine, and for C jump to jump back. So here I just want to say data and 0, 0. So for now, I'm not going to jump. So this is going to be just the one iteration. It's not going to be reflected on the printed board for now, but the values of the X and Y registers would be dumped into Y would be dumped to F4. X would be dumped to F5 0 page. So we need to make sure that the values there are correct. Okay, so going back to addressing mode, so 0, 3, 0, 0, and I click go. So now it's waiting for user input. So we have the stones that has been placed on board. So let's play the stone somewhere at AA. We just because now it's printed the board. Now it's waiting for the user input. After I provide the user input, it will call the count. It will initialize the X register to 22. It would set the variable C color to 4F, and that it will call the count. Okay, so let's say A and A. Okay, and we stop here. We exit the program because the loop is not going anywhere. We do not reprint anything. So now let's see where the liberties are. So 1, 2, 3, 4, 5, 6, 7, 8. So the value of the Y register should be 8, and the value of the X register should be 22 because we started from here. So let's go to 0, 0, 0, 0, F 3. This is the A register. This is the A register. So Y register 8, which is exactly the case. 1, 2, 3, 4, 5, 6, 7, 8. And the X register contains the value of 22, which is exactly the case. Great. So now when we're sure that all this works properly, we can loop back every time in the main loop just to visually see how the liberties would be marked with plus symbols there. So I go to 0, 3, 0, 0, and okay, set the color, call the count, and here for C, data for C. Going back to address 0, 3, 0, 0, and go. So A, and now we print the board again because we loop back. Now you see the plus symbols to represent the liberties. So, and also the stones are no longer uppercase, but now they are the lowercase o. You see, like the uppercase o is this one. I just put the stone into AA, and the lowercase is this one. Essentially, I can put more stones, but yeah, we're not changing this, so it's like all fine. So what else can we check here? So we can check if the off-board detection is working. So instead of putting the stone here and here, we might put them here and here. So let's quickly try that. So just stop, reset, 0, 3, 0, 0, and 85, 22, and 85. Instead of playing 23, let's play 21. 21. Now this stone goes here, and 24. This should be 1, 2, 12. Let's make it 12. So now this stone goes in here. Okay, go into address 0, 3, 0, 0, and go. And so the formation of stones has been changed. Okay, now let's just play something. Now you see offboard detection works. Okay, stop. So we can play more. So we did not stuck. We are still within the main loop. Great. So the liberties are marked properly. Okay. Yeah. So we can also check if edge detection in this corner is working properly. So we can change these three values to EE, EF, and FE, and also loading the value of EE to the A register initially. So let's quickly do that. 0, 3, 0, 0. Okay, so start with EE. Then this one is EF, EF, and this one is FE, FE. Calling print board, calling get user input, and here not loading 22 to the X register, but EE, since that's the value that we're looking for. Essentially, we could also load FE or EF, FE or EF. That the result would be the same, but yeah, let's just load this one. Okay, so going back to addressing mode 0300 and go. So you see, like now we have the stones in this corner, and let's do A, and exactly the same stuff. Yeah, 2, 2. So the stones that are connected within a single group has been marked as connected stones, so no longer uppercase but lowercase, and also all the liberties they have has been marked appropriately, which means that the count routine is working properly. So yeah, guys, this is it from my side. Starting from the next video, I would be doing things related to capturing stones, the routine, white effect, the next part from the pseudocode by John T.K. Millen. So hopefully that would be even more exciting. Now, this is it from my side. Thanks for watching. I'll see you next video. Until then, and cheers.